Hello, I'm Chia-Yu. Today I would like to share with you a very powerful analytical technique called isothermal titration calorimetry, also simplified as ITC. Hope after this short video you could briefly understand how does it work and how to analyze the ITC data. Simply to say, ITC is a technique used to determine the thermodynamic properties of chemical or physical equilibria. ITC could provide affinity constant, the stoichiometry, enthalpy, and entropy of biomolecular interaction in a single experiment. The theory behind ITC is not very difficult to understand. The foundation of this technique is based on a simple measurement of heat. Because of the relationship between the change in enthalpy and the change in internal energy, which is delta E of a system, the heat absorbed or released is equal to delta H when the system is at constant pressure. Heat exchange is present in essential of physiological process, making this technique particularly relevant in understanding binding equilibria and other molecular processes. Okay, so now let's see how does it work. The major component in ITC are two cells. Reference cells usually contains water and the other contain protein and is called sample cells. And ITC will keep these two cells at exactly the same temperature. Between two cells, there is a heat sensor help to detect temperature differences between reference and sample cells, and feedback to the heaters. At the beginning of this experiment, reference cell and sample cell are set to the same desired experimental temperature. At the above of the ITC, it equipped with a syringe, which is a very accurate injection device. It allows add a specific number of ligands, often are small molecules, into the sample cell contain the protein of interest. If there is a binding of ligand in the protein, the heat changes that are detected and measured. Take an exothermal process for example. As for the first injection is made, the ITC will measure all heat release until the binding process has reached the equilibrium. In this exothermic case, this heat is given to the sample cell, and as the temperature of the two cells come back to the same, the signal will return to the starting point. With adding more and more ligand, and the ligand-protein ratio is increased through the series of injections, until all the protein reach saturation, the heat changes start to decrease. The area of each peak is then integrated and plotted versus the molar ratio of ligand to protein. The resulting isotherm can be fitted a binding model from which the affinity is derived. The molar ratio is at the center of the binding isotherm gives us the reaction stoichiometry. The delta H is also derived directly from the isotherm and is the amount of heat released per mole of ligand bound. This means that the single ITC experiment is able to provide us binding affinity, stoichiometry, and all thermodynamic properties, including free energy, enthalpy, and entropy. The thermodynamic profiles provided by ITC could give us an insight of protein-ligand interaction, which plays a very important role in drug discovery. For example, I have synthesized this type of immunocyclatose as a glycosidase inhibitor. By using ITC, my collaborator and I found with the aliphatic chain get longer, entropic term is increased because the aliphatic chain could kick out water molecules and form a stronger binding with the hydrophobic channel in the protein. Similar in this case, two molecules both has a fluoro substituent but on different position. The ITC data suggests that the binding of two compounds to the protein was enthalpy driven. However, when compared to 2-fluoro, the enthalpy gains of 6-fluoro are more significant due to the presence of complete water molecule network and a stronger interaction with the surrounding residues as well as water molecules. In contrast, the binding of compound 1 harvests the more advantaged entropic term ascribed to the distortion of the water molecule network compared to the compound 2. Accordingly, the complex structure associated with the thermodynamic data demonstrates that the water molecule network in the binding pocket of the protein should be taken into consideration in the process of the lead discovery. Furthermore, the thermodynamic of binding is influenced by multiple factors, including hydrogen binding and hydrophobic interaction, dissolution, residue mobility, dynamic, and local water structure. ITC could help understanding the effects of this factor and applying knowledge in drug discovery. Here is an example of the scientists utilize ITC technique to do the fragment-based drug development. In a nutshell, ITC is a powerful tool for categorizing interactions, especially interactions of biomolecules in a broad range of binding affinities. Hope this short presentation could let you have a general idea of these techniques. Thank you for your listening.